So this problem, how much energy is needed to completely vaporize a 3-gram ice cube initially at -4 degrees Celsius? So we have a little ice cube. We need to get it to its melting temperature and then melt it and then get it to its boiling temperature now that it's liquid water and then vaporize it, turn it to gas. All right, so let's see here. When we go to our test notes, water and ice are right next to each other, so we have these C values for water and ice. Notice melting temperature, boiling temperature, latent heat of fusion, and vaporization are only listed on the water row. But again, water and ice is just a different phase. Since our water is not yet at its melting temperature of 0 degrees Celsius, we need to put energy in to get it there. And then we need to account for the energy to actually melt the ice, turn it into liquid water. And then we need to get that to its boiling temperature, where it can start changing phase from liquid water to gas, and then we need to account for the energy to turn it into a gas completely. So we will need these values. Oops, that's the wrong program. So I'm just going to write all these values down. So C of ice, 2090 joules per kilogram Kelvin. C of water, 4190 joules per kilogram Kelvin. The melting temperature of ice or water, H2O, 0 degrees Celsius. Boiling temperature, 100 degrees Celsius. Latent heat of fusion, 3.33 times 10 to the 5th joules per kilogram. Latent heat of vaporization, 22.6 times 10 to the 5th joules per kilogram. So it ends up being multiple steps, because we're starting at an initial temperature of -4 degrees Celsius. Oh dear, sorry about that. So we have this initial temperature, we have an ice cube, so we're in this solid phase. We have the mass, which we will want to be in kilograms, because the units on our C and our L's are in joules per kilogram, or joules per kilogram Kelvin. So Q1, the first step is to put enough energy in to increase the temperature to 0 degrees Celsius. We need to get this ice cube to its melting temperature where it can melt. Since we're changing temperature, this is going to be mass of the ice, C of the ice, times delta T of specifically the ice itself, while it is in the, that is ice, while it is in this solid phase. Once we've put in this amount of energy, we still have an ice cube, but we have an ice cube at 0 degrees Celsius. Once it is at its melting temperature, we need to figure out how much energy is needed to melt this ice cube, meaning change it from a solid phase to a liquid phase. This represents a change in phase, so we need the M times L. It will be positive because we do need to put energy in order to break the bonds and go from a solid to a liquid. So the equation for changing phase specifically is M times L. We want latent heat of fusion, L sub F, because we're going between the solid and liquid state. I'm going to write this down here as well. So mass of the ice times latent heat of fusion. I'm essentially writing out a total energy we need to put into this system. All right, so as a reminder, after this much energy, we still have an ice cube. But it's now at 0 degrees Celsius. So when we plug in the mass of the ice, C of the ice, and the temperature change of the ice, we'll still have the ice cube at 0 degrees Celsius. We have to put in this M times L energy to now have liquid water. The ice cube has melted, but it's still at 0 degrees Celsius. We have not put in enough energy to change its temperature. So the next step, our Q3, would be to put the energy in to increase the temperature from 0 to, well, we're trying to turn it completely to gas. So from 0 to 100 degrees Celsius. Since we're changing temperature, I'm going to leave this as mass of the ice. Even though it's now liquid water, the mass doesn't change. The density and volume change, but the mass stays the same. So I'm going to leave it as Mi. But because it is liquid water now, it's in a liquid phase, we need to use C of the water, and then the change in temperature it goes through while it is water. So this is liquid water going from 0 degrees Celsius to 100 degrees Celsius. But that doesn't boil it off. That only gets it to the boiling temperature. So we want to completely boil this water off. That's what we mean by completely vaporizing the ice cube. So we need one more term. We need a Q4 to boil. We need to vaporize all the liquid water and turn it all into gas. So we need the energy required to change it all from liquid to solid. Just kidding, sorry, liquid to gas. So L sub V is needed, vaporization. So change liquid to gas. It will still be at 100 degrees Celsius. If we wanted to make it hotter, we would have to add another term that would account for increasing its temperature once it's at a gas. But that's not what we're doing here. So the total energy needed. Technically, we could factor out the mass of the ice. It's the same in every term. I don't know if you want to or not. It doesn't particularly matter. Okay, so our ice in kilograms, 0.003 kilograms. We have to multiply that by the 2090 C of the ice, the change in temperature the ice goes through. Well, the ice itself starts at -4 degrees Celsius and it goes to 0 degrees. So the final temperature while it is still an ice cube is 0 degrees Celsius minus the negative 4 degrees Celsius. So we're going to get a positive number in there. So the 4 times the 2090, that's the times the mass is going to be the energy needed to just get the ice cube to 0 degrees Celsius. Then we add the energy needed to change phase from solid to liquid. Now we have a liquid, so we need to use the C for the liquid state of water. We're going from 0 to 100, so 100 degrees Celsius is the final temperature, minus the initial of 0, plus, finally, the energy needed to vaporize it completely. The kilograms will cancel with the kilograms either in C or L. Let me plug in these numbers, and then one other comment. 90 times 100. So I'm getting 9061, so about 9.1 kilojoules of energy are needed. Now, as I mentioned before, the kilograms are going to cancel with the kilograms in these units. As a reminder, I did leave my delta T's in Celsius. But for example, for the ice, T final is 0 degrees Celsius, which would be 273 Kelvin. T initial was negative 4 degrees Celsius, which would be, 269 Kelvin. Delta T is 4, regardless of whether I had my temperatures in Celsius or Kelvin. That's true for delta T of the water. That's true for delta T of anything. Because the conversion has us adding 273 to both initial and final temperature, you can keep both initial and final temperatures in Celsius and take the difference, or you can convert them both to Kelvin and take the difference. You'll get the same difference. You do have to make sure they're both in the same measurement system, though. I mention that because I've often seen students convert one of them but not the other. So just make sure your temperatures are either both in Celsius or both in Kelvin, and then the delta T will be correct.